So, hi everyone. Today we will be discussing a very important research paper published by Microsoft that is introducing a new technique called as rStar-Math, which enables smaller LLMs to master mathematical reasoning using self-evolved deep thinking. So, I will be explaining all the stuff how rStar-Math works. The best part being is that now 3 billion models, 7 billion LLMs can beat out models like GPT-4o and even O1 mini on mathematical benchmarks. So this is the powerful algorithm, the approach that the team has shared. So what is rStar-Math? Let's start by that. It helps small LLMs, SLMs that we talk about, to become really good at solving mathematical problems. Normally what happens is that models like GPT-4 or Claude 3.5 Sonnet are great at mathematics, but they usually require a lot of computing power. Now we need to understand how rStar-Math works. This is a little complicated and I would wish you to focus a little here. So there are multiple steps involved. So the first is a deep thinking with Monte Carlo tree search, that is MCTS. So just read this particular point. In case of rStar-Math, we will start off by assuming multiple paths to solve a problem. So if you remember trees of prompt, trees of thoughts, the same thing that we would be doing here also. So instead of thinking in just one direction, we will start off with thinking in multiple direction. And then as you can see here, at each step, the model generates possible steps, like writing down the equation to solve the mathematical problem, and checks if the step is correct by running a small piece of code. So this is an interesting part that they have introduced, which they call as code augmented chain of thought. So it's not just a chain of thought, but they are also introducing codes to verify whether the thoughts are correct or not. So if you are not familiar about what is Monte Carlo tree search, I think quite easy. If you read it here, if you're playing a game of chess and you're trying to figure out your best move, you don't think what your opponent will do. So you think ahead like this: if I move X spaces, then he might move Y spaces. So you're trying to think of all the possible scenarios in your mind and then thinking of, okay, this is the best which leads to. Monte Carlo research works in the same way. What the team is using in the research paper for rStar-Math: explore possible moves, simulate outcomes. Okay, if I follow this path, what will happen? Learn from your results and then choose the best move. Very, very easy. The most important part that the paper has introduced is code augmented chain of thought data synthesis, as mentioned. It's not just chain of thought, but with code execution as well. So every thought they are doing, they are trying to write a question and then write a code for it and then try to execute the code. If the code works well, then they move in the right direction, else not. Then they have also introduced a concept called as self evolution. I'm not jumping deep into the concept of self evolution, but giving you a brief, it is a mechanism similar to teaching a student how to learn maths. So you start off with basic problems, learns from them, and then uses that knowledge to tackle harder problems. So this is what self evolution is all about. This process repeats, and with each round the model becomes more smarter. And the last one is a process preference model, that is PPM, that the team has introduced. So it's more of a reward model. If you have been into reinforcement learning and if you know our different techniques that are used to train models, usually you will see a system called as reward models. These reward system help the model decide which steps are good in the chain of thought and which are bad. So instead of looking at just the final answer, it also looks at the entire reasoning process. It helps the model to learn from its mistake. Now let's see an example for code augmented chain of thought in one of the images shared in the paper. So if you see here, if you see at the top, given that positive integer some equation is given, what is the value of x and y? So this is how it might start in the thought. Define variable x and y. Here you can see they are mentioning a ppm score also. So the ppm score is less. Define the equation, solve the equation for y in terms of x. So this is how the thought process is going on. Now just see here, if the answer for a thought is wrong, you can see the ppm score going very negative, minus zero point 0.5. Think out of the box, find an easier solution, and it might go for a easier solution now. So there are multiple thought chain of thoughts that are going on. One is wrong, one is right, and they are writing codes for that. As you can see, the ppm score is quite high if the code executes. So the code is executing, they are moving ahead in the steps, they are again executing the codes and then finally getting to a final answer. Here you can see that. Now moving back to our presentation. Now we'll try to understand rStar-Math using an example. That should be quite easy. So let's say the model, R star math trained model is given a problem. Find the value of x that satisfies the equation 2x plus 3 equals to 7. The first step might be the model writes down the equation and say I need to solve for x. Then Then it generates an equation like this, as you can see. The Python code to solve the equation, the code runs and outputs 2, which means x equals to 2. The model checks if the step is correct by running the code and writes the final answer. Now, for example, if the code that is written doesn't give you an answer, this means that the thought process is wrong in this case. And then it will discard the entire thought and then move on to a new process. This is how R star math, like in a layman terms, works for you. Now, how rStar-Math is enabling math mastery? This is very important because if you can think of the paper is headed like this, that enabling small LLMs for maths mastery. First of all, breaking down the problem. So in mathematics, when you are solving a complex equation, usually you need to break it into step by step. So rStar-Math looks to be very, very apt for it because as you can see, you, you go for chain of thoughts and then execute codes as well. Verification using code, I think this is a great add-on. To be honest, why I'm not sure why I never got this idea, but looks crazily good. Self-improvement, the self-evolution topic that we discussed, the model improves itself over time by solving increasingly difficult problems, and it focuses on the process and not just on the answer. The process preference model, as you were in the diagram that we shared, there was ppm score given for all the steps. It was not evaluating just the answer. So this is the best part. So the model it ensures that the model learns to reason correctly and not just to output an answer. Now we will be talking about certain performances and metrics in the metrics table shared in the paper. So this is a pretty huge metrics table that the team has shared. Just look for the blue ones. As you can see, rStar-Math 3.8B SLM 7B ppm. So 3.8B SLM means that the LLM used is 3.8 billion parameters, that is 5 mini instruct, as you can see here. And the 7B ppm is the reward model that is used, which is of 7 billion parameters. So here you can see that these are the results. If you compare it with GPT-4 O mini, let's take one of the models. On maths, the score is 90 on math dataset. Now, if you look for rStar-Math 64, that is 64 iterations, 7B SLM plus 7B ppm, the score is same. So this is crazily good. And for other model also, like if you look for 1.5B SLM and 3.8, the scores are not that bad, 86.4 and 88.6. Similarly, for O1 mini AIME, that is an international level maths Olympiad score, 56.7, and if you look at it, it's 53.3. For a model of just 7 billion parameters to giving close competition to O1 is just crazily good. AMC is 95, as you can see, it's 87.5. The models are not lagging way behind. It's minor issues, minor discrepancies are there, but not much. In Olympiad bench, 65.3. Here 65.6. It has even outperformed O1 Mini on Olympiad bench. Gaokao in English 2023. Here it has outperformed O1 Mini by a decent margin, 78.4 to 81.3. You can just stop on this particular screen and compare it with other models like GPT-4o, Claude 3.5 Sonnet, O1 Preview, O1 Mini, and the different combinations used. So they have shared results for 5.3 Mini Instruct, Coin 2.5 Math, Coin 2. Coin 2 Math 7B, and Coin 2.5 Math 7. You can compare these results. rStar-Math results are pretty good. You don't want to miss out on this particular approach that Microsoft has shared. Now, coming towards the end of this entire tutorial and the paper review, why rStar-Math is important? So, it is introducing quite a few things. First is efficiency. When a small sized LLM is outperforming big size LLM, we are not just saving, we are saving a lot on cost because big LLMs require extensive computing power, if you remember. Accessibility, smaller models are accessible on any device. You can run a 7B model very easily in your system, but not a GPT-4 sort of a model. And scalability, I think the major limitation with LLMs right now is deployment part. But if you are able to empower smaller LLMs with this much power, I think that deployment won't be soon an issue. So with this, we would be concluding this particular tutorial. I hope you understand rStar-Math. The inclusion of code generation and execution is a big add-on, I would say. and the results are looking crazingly good. Let's see if some models are released with R star math variant, and then we would be more sure about it. Thank you so much.